Hello and welcome to another video in the OCR GCSE computing course. We're looking at how you represent numbers in a binary format in this data representation chapter, and I'm splitting this topic into two videos because as you'll see there's a lot to cover, and this would sort of be taught over quite a few lessons and it wouldn't really do it justice to do it in one video. So to make sure I cover everything and I'm as clear as possible, I'm doing it in two videos for one topic. So first of all, a little recap again, but with some of this is new stuff. Binary is base 2, Denary is base 10. And the decimal number system we use is also called Denary. So Denary is decimal, it's what we use, 0 to 9, those are our numbers, because it's base 10, those are 10 digits. And you need to be able to convert positive integers, so whole numbers, from 0 to 255 to binary and back again. That's not all from 0 to 255, that would be a bit much. They'll give you a random number from 0 to 255. Almost this is nailed on to be in your exam. They'll give you a random number, probably quite large, probably 100 and something, maybe 80, something like that. And you have to convert it to something, and most likely binary. So first of all, we're going to look at how you convert between Denary to binary. So first of all, let's look how you can convert 7, the positive decimal number 7, as a nibble to binary. So we know that a nibble, firstly, only has, it's 4 bits, so 4 binary digits. We know it from the last video, a nibble has 4 binary digits. So what I would do, my method, is I draw however many boxes as we're asked to do. So a nibble is 4, so a table of 4 columns and 2 rows. That's what I do, and then I'm going to label my columns. So let me show you how to do this. I'm using my graphics tablet again, so I apologise for the poor handwriting. So what we do, we start it with 1. All numbering systems start with 1. In decimal, in Denary, you go 1 times 10, 10, 100, 1000. And we're doing base 2, so basically we multiply by 2. That's only the case for this, we don't always multiply by 2. Essentially what's happening is we go 2 to the power 1, 2 to the power 2, which is 4, and 2 to the power 3, which is 8. And if in effect in binary we're timesing it by 2 each time. You can't do 1 to the power 2 because that's also 1. 1 to the power a million is also 1. So yeah, so we have our columns here, and what we're doing, we're looking to find the number 7 as a nibble. So what we do, and I'll just do it and then you can hopefully see what I'm doing. First of all, I go, does 8 go into 7? 8 does not go into 7. Does 4 go into 7? Yeah, 4 goes into 7, remainder 3. Does 2 go into 3? Yes it does, remainder 1. Does 1 go into 1? Yes it does. Like that. That's what I'm doing. And what this represents 8 times 0, so we're timesing from our columns to our rows. 8 times 0 plus 4 times 1 plus 2 times 1 plus 1 times 1. That may seem like a weird way to look at it because 4 times 1 is redundant, that's just 4. 8 times 0 is redundant, that's just 0. So we're just doing 4 plus 2 plus 1, which equals 7, as you can see, and that's represented by 0, 111 in a nibble format. If we were asked to represent 7 as a byte, we would just do 4 extra zeros at the end. But this representation is useful for the next couple of things, not on this slide but on the next. So let's move on, let's have a look at a slightly harder example. We're representing 28 as a 6-bit binary number, so we have 7 column heads. I've just done it, so it saves me doing it again. So we've got this far, we're doubling it, and we double it again to 16 and double it again to 32. Incidentally, they won't always ask you to do it specifically as a 6-bit or 4-bit or 2-bit or 20-bit, whatever. They won't ask you to do that. Sometimes you just have to keep going until you get to a number that doesn't divide by it. So for example, 32 here does not go into 28. It just does not. So if we were doing this and we weren't told it has to be 6 bits, this is 6 columns, we would just not include this, but we've been asked to do 6 bits, so we'll respect what they ask us to do, otherwise we'll lose marks. So this doesn't go in, first doesn't go into 28, 16 does go into 28, and the remainder is 12, that took me a while, and 8 does go into 12, it goes in once, and the remainder from 8 into 12 is 4, and we've got a 4 here, so 4 goes into 4, 1, and we've got nothing left over, so these are both 0. And that is your answer, 0, 1, 1, 1, 0, 0. Okay, finally let's do a harder one. So we're looking at 201 as a byte. So a byte is 8 bits, so again we do 8 columns, and here we're extending it further to 64 and to 128, sorry. So go slightly harder, and again we work from left to right. This is my method. There are lots of methods. If you don't understand this, I'd recommend you look at other YouTube videos who may explain it better than me, because I'm not a maths teacher. Maths teachers are really good at explaining this sort of thing, because although I understand the maths behind it, I'm not particularly good at explaining it as well as I can, but hopefully this is sort of useful. So 201 as a byte. Again we do 128. Does it go into 201? No, it doesn't. Oh, sorry, no, of course it does. 128 does go into 201. You've got to really be careful with this. So I made a mistake that would mess up my whole calculation. That's a really bad one as well. So 64, sorry, 201 minus 128 equals, what does it equal? 201 minus 128 equals 73. So does 64 go into 73? Yes, it does. And then 73 minus 64 is 9. So the remainder is 9 from that. And does 32 go into 9? No, it doesn't. Does 16 go into 9? No, it doesn't. Does 8 go into 9? Yes, actually it does. Remainder 1. Does 4 go into 1? No. Does 2 go into 1? No. Does 1 go into 1? Yes, it does. And that is our answer. 11001001. Great. Okay, let's move on. Let's look at doing the vice versa. Let's look at doing the inverse, which is going from binary to denary as opposed to denary to binary. So we're doing the opposite, but this is slightly different, so it's important that we know how to do this. So our example is convert 00110010 to a denary integer. So we've got our table here, going a bit too far. We've got our table here, and I'm going to fill it in how I would do. So first of all, because we don't know how many columns we're going to have, let's fill in this. We know, you can see immediately it's a byte. I forgot to mention maybe in the last video, but usually a byte is separated by a space. So let's fill it in. 0, 0, 1, 1, 0, 1, 1, 1, 0. That should be a 0. And let's do that again. Again, it is easy to make mistakes. You've really got to be careful what you're doing, but otherwise it's quite an easy process. So me just losing track of my focus a bit has led me to make a couple of mistakes. Okay, so we're filling it in like that. And now let's do our column headings. So start off with 1, times it by 2, times it by 2, times it by 2, 16, times by 2, 32, 64, 128. And you'll never get asked to go further than 128. It's only ever going to be as large as a byte. So this is our information we have. And now I'm going to work backwards. Like I mentioned before, how you represent it by essentially what this is. I'm not going to do the zeros, but 128 times 0 plus 64 times 0 plus 30. Oops. Gone a bit too high there, not allowed to go that high. 32 times 1 plus 16 times 1 plus 2 times 1. And what we do, 32 clearly times 1 is just itself, plus 2. 32 plus 16 is 32 plus 16 is 48, plus 2 is 50, and that is our answer. 50 is our answer for that calculation. Okay, let's move on. So one thing I was gonna show here, just because it saves me time in a second. The one way of working this out. Oh, I can't go that high. Let's just delete some of this stuff. Right, so essentially, this is going over myself, but 32 plus 16 plus 2. We can do this using the addition method, and hopefully we're done with some maths, but 6 plus 2 is 8, plus 2 is 10, so we have an extra one here, and we do 3 plus 4 equals 5, which is our answer again. And this will be useful when we move on to the next thing, which is about adding in binary. So you're required to know how to add two 8-bit binary numbers and explain overflow errors if they occur. So we've got 3 examples here to go through. Let's change my colour to light blue to represent this A. So this is a really easy example, and I'll show you why it's really easy in a second. It's literally just adding how it would be in normal maths. So go along. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 0 is also 1. And that's our answer. And we can double check this. This equals 12 in binary because we have 4 plus 8, and this represents 2, and this represents 14 in binary, because that's 2 plus 4, 6 plus 8 is 14. So we know that that works. It gets slightly more complicated when we move on to our next example here, which I'll represent with yellow. So let's lay it out how we did before. I'll try and be as neat as possible. Make sure I don't miss out any bits. And then let's line it up like you would in normal. Okay, so let's start off by normal, and straight away we've got a problem. 1 plus 1 equals 2, but we can't use that in binary because it's only 2 digits. In this case, 2 doesn't exist. So what we do 1 plus 1 equals 10. Doesn't make sense, but it actually works. So if we count it as 10, we put a 0 here and we put a 1 above. And 1 plus 0 is 1. So it sort of evens itself out. Then we have it again, 1 plus 1, and we do equals 10. And we put the extra 1 in the next column. Then we have 1 plus 1 again, plus 0 equals 10 again. And we have to do this once more, and it's going to keep going, unfortunately. 1 plus 1, so 10 again, and we keep going. It may take a while, and these look like 6s, they're not. So if I need to put another one here, and then finally we end this little streak of having overlaps, overflows, which are overflow errors. So 1 plus 0 and plus 0 is 1, and then 1 again, and that's our answer. And again, I've written this down actually because it take me a while to work it out. 45, that equals 45, and this equals 149. And this in binary equals 194. You're welcome to check that, but it does work. If you add them together, it equals 194. So that's evidence that it works using that overflow error. And again, there are plenty of videos of this. If you are confused, if you're not satisfied in my explanation, which is fine, I won't take offense to it as long as you understand. So finally, let's do a hard example. We're not going to do the end bit for the sake of time and space. So let's do this one. A slightly larger number. And I've noticed I've missed a 0 out there. In fact, let's just... Okay, sorry, apologise. 11101110, and then we have 00111101. And if you're wondering how many marks these sort of questions would be, there might be 3 or 4 marks even if you're lucky, and they should be quite easy marks. So let's do this. 0 plus 1 is 1, easy. 1 plus 0 is 1, and now we have 2 1s which we're going to count as 10, and now here we have 3 1s, and this is where it gets a little more complicated still. We count this as 11. It's not 11, but we count it as if we're doing 11 using this addition method. So 11, so we put a 1 here, and we also have to carry a 1 as well. 1 plus 0 plus 1 is 10, as we mentioned, and then we have this again. So we have put a 1 there, keep carrying for 1, we're going to keep carrying for 1, and we even have an overflow, so we extend. And you have to be able to explain these overflow errors. Again, I wrote this down just so it's easier for me. This equals 238, this equals 61, and in total they equal 299. Great. So that's what we're covering in today's video. That's everything you need to know about binary. So that's half the topic. Next up, we're going to look at the next half of this topic.